Now, when we're talking about series and trying to determine whether or not they converge, most of the time we're not going to find what the series converges to, what the sum is. We're not going to find a number. We're just going to make a determination whether or not the series converges. However, sometimes we can find the number that the series converges to. We're going to look at a couple of cases. In this video, I'm going to look at a telescoping series. So here we go, telescoping. Now, you'll see why it's called a telescoping series here in just a minute, but let me show you an example of one. Let's suppose that we've got this series right here, 1 over n squared plus n. And we want to make a determination. Does that series converge? And if possible, we'd like to find out what it converges to. Okay, so here's what we can do. Here's one technique. We notice that we could factor the bottom and get it in this form right here, okay? That form, okay? In other words, we factor the bottom. So we see a series, and one of the things that jumps out at us, we could factor that bottom, and then here's the trick. With these telescoping series, what you're going to do is you're going to use partial fraction decomposition to write this in this form right here. So what you want to do is you want to rewrite this in this form. Okay, so you can harken back to when we were integrating with partial fraction decomposition. So we want to decompose this fraction. Now you remember how to do that. Here we've got, you can see the common denominator here would be n times n plus 1. So what we're going to have is, if you look at this, you're going to have a times n plus 1 over n times n plus 1. See, for this first a over n, I needed an n plus 1 on the bottom, so I multiply the top and the bottom by n plus 1. And then for the b, I just need an n. Okay? So now we have the same denominators, so remember we can put the numerators together, and now we have this situation. Yeah. Now there's shortcuts to this, of course. I'm just, acting like you haven't seen this in a while. So here's what we have. Now, if these two sides are equal, if the left and the right-hand side are equal, then, and the denominators are the same, I can just focus on the numerator. So what I have is 1 equals a times n plus 1 plus bn. And I'm just going to equate coefficients. So I've got 1 equals a n plus a plus bn. See, I cleared my parentheses. Now, notice that I can group the n's together. So I've got 1 equals a plus b n. See, I just put this and this together, plus a. Now, the thing is, there is no n over here with this 1. So a plus b must equal 0. However, a we know is 1 because that's the constant. So if a is 1, just right here putting a 1 in for a, you get that b is equal to -1. Okay, good. So now we have this situation here. We have the sum from n equals 1 to infinity of 1 over n times n plus 1. We could rewrite that as this. We can use its decomposed form. Whoops. Yeah, there it goes. Now, this decomposed form is what I want to use because what I want to do is I want to start generating the partial sums. And I want to look for a formula for the sequence of those partial sums. So let's look at this. Let's look at the very first partial sum. That's when I put a 1 in for the n. So what I get here is I get a 1 over 1 minus 1/2. That's the first partial sum. Now I want to look at the second partial sum. Now I'm going to have the first partial sum, but I'm going to add the next term. The next term is when I put a 2 in for the n. So dig this now. I'm put a 1 over 2 minus 1 over 3. See, I just put a 2 in there and a 2 in here. Yeah. Now, here's the cool thing. Notice these things cancel. And what I get is 1 minus 1/3. Yeah, that's it. So that's the second partial sum. Now, let's see what happens when I get the third partial sum. So the third partial sum, I've got the second partial sum, and then I put in the 3. So I get plus 1/3 minus 1/4. And once again, dig this, you get 1 minus 1/4. Now, what I want to do, my whole goal here is to find just a general form. Okay. I've got 1 minus 1/2. Let's see what that might be. Well, I could look upon that as 1 minus 1 over 1 plus 1. This one right here is 1 minus 2 plus 1. This is 1 minus 1 over 3 plus 1. Now dig this. Notice that this 1 corresponds to that. This 2 corresponds to this. 3 and 3. It looks like I've got a pattern here. And I could say, well, let's look at the kth partial sum. It's going to be 1 minus 1 over k plus 1. So that's the kth partial sum. So we've got this series, this sequence this is the general form. So we could now determine what that series converges to by looking at this limit right here. This limit right here. Whatever that limit is, that's what that series converges to. Now, if this limit diverged, if this limit didn't exist, then we would say, okay, the series diverges. But if this limit exists, then we found that our series not only converges, but if we get that number, then we know what it converges to. So if you let k go to infinity, notice what happens. This term right here, that just goes to 0. So what you're left with is 1. So what we say is this. We say that this limit, or this infinite series, is equal to 1. So we found that it not only converges, but what it converges to.